Okay, thanks Sanjay, and thank you for coming. I know there are many talks today in different parts of the engineering college, so you're too busy, or some of you are too busy. So, in fact, when I thought about this talk, it wasn't clear to me who I'm going to give the talk to. So what I decided to do is to talk about a line of work that my group has been working on, or one of the lines of work that we've been working on for the last few years, that has to do with both learning and inference in natural language processing. So there are several of my current and former students that are involved in this. And as you'll see, I'm going to talk a little bit about the research and also spend some time giving basically a tutorial on some of these topics here. I already see in the audience that some of you don't need this tutorial. Hopefully some do. And it will allow me to an easy way to answer some of the questions that people from UPCRC, for example, ask about this kind of application. So anyhow, I want to start by telling you about the problems that I want to solve. Here is a short story. You can quickly read what it says. And really what eventually we want to be able to understand this story. And without getting into a definition of what does understanding mean, this is taken from a test, a comprehension test that second or third graders are taking in many elementary schools in the US. And you can see that once they've read the story, or you have read the story, and when you're given a small number of statements or questions about the story, it's rather easy for you to determine the truth value of these stories, of these statements given the story. So it's rather easy to figure out whether Christopher Robin was born in England and so on. The question is, can we write programs that do that? And this is really the goal. If you start thinking about this, what does it mean for you to be able to answer these kind of questions or determine the truth value of these statements? You need to do a lot of things. For example, you need to, looking at this story, you see a Christopher Robin here, there's Chris here, there's Mr. Robin here. Do they represent the same person? Think about it a little bit, and you'll see that the answer is no. You can look and see that there are many pronouns in this sentence, and in this story, in order to understand what's going on, you need to figure out who is this he, what is this him, who is this he, and so on, and link them to other entities in this story. You need to be able to look at some statements, some relations, like someone wrote a poem, someone wrote a book, someone has written 2 books. You need to know who did what to whom in order to understand what's going on here and be able to figure out how to address this statement. So basically, overall, there's a lot of standalone tasks. Each one of them is non-trivial in its own, but we actually have to put this together in order to understand what's going on. So there are multiple, what we call context-sensitive disambiguation problems that one has to solve here, and moreover, one should be able to make some global decisions that depend on solving at some level these disambiguation problems. And we typically view this global decision as constraint optimization problems over these learned variables. So now that you do this, I mean, if you want a simpler instance of this problem, you can try to read this statement. What does it say? Nice to meet you too. So it's very easy for you. However, if you think about what you did is really a similar process to understanding the story. A little bit more abstract, somewhat different, much easier. And I have no clue how you did it, but consistently people take just a few seconds and understand it. And at some abstract level, you could say that you brought from home with you different models for different parts of this picture. Each one of them probably wasn't a unique a model with a unique decision. You had several options for each one of the components here, but when I put this together on one slide, and when I ask you this question, you were able to constrain it enough so that each one of them got one interpretation, and what's written here is quite clear. And this is really the type of problems that I'd like to talk about here. So we're interested in solving global decisions where several local decisions play a role, but there are mutual dependencies on their outcome. So you could think about each subproblem or each component as a problem that requires us to learn or program a model or a classifier. And our goal eventually is to incorporate these models' information along with some prior knowledge or constraints in making coherent decisions. And by coherent decisions here, I mean decisions that on one hand respect the local models, and on the other hand, they respect domain and context-specific knowledge or constraints. So in natural language processing, for example, these problems are typically called today structured output problems, where you have multiple dependent output variables. However, we think about it in a slightly broader context, because in some cases, some interesting cases, not all the local models can be learned at the same time. Key examples would be the example that I started with, story comprehension or textual entailment or question answering. And in some cases, constraints will appear only at evaluation time. You don't have them when you learn. So the model that I'm going to discuss here is something that we call constraint conditional model. It's a general framework that combines learning conditional models with the use of declarative expressive constraints within a constraint optimization framework. So basically, you can think about formulating the decision process as a constraint optimization problem that we do by first breaking up complex problems into a set of subproblems and require that the components' outcome are consistent modulo some constraints. So this paradigm or this framework has been shown useful in the context of many natural language processing problems, including semantic parsing, summarization, co-reference resolutions, transliteration, and so on, both in works that my group has done and quite a few other authors in the field. So I want to introduce this model, provide mostly motivation and some examples without getting into the details too much. And really, most of my talk today I'm gonna use it to give a very quick tutorial on some of the computational processes that are involved in this. So, for example, I'm going to talk about mostly classification, a little bit about the inference, pipeline issues, and scale of problems. And my goal is really for those people that are not working directly in this domain, but more interested in thinking about it from the perspective of building systems or programming languages or architecture or parallelizing these, they'll get some feeling for the computational problems. So if I have time, after this tutorial, I'm going to give you some quick view of some of the current research questions in this line of work, mostly things that have to do with training paradigms, basically looking at different ways to train models, different ways to incorporate training with inference, and several possible paradigms and what are the trade-offs between them. And please feel free to stop me at any time and ask questions. I have many slides. I don't need to go over all these slides. Okay, so let's start with a very simple example. And this example comes from information extraction. Our goal here is, given sentences, to recognize in the sentences entities and relations between them. So in this simple example, you see the sentence, Doll's wife, Elizabeth, is a native of North Carolina. We want to know that Doll, in this case, represents a person. Elizabeth, in this case, also represents a person. This is a location. And there are relations between them. And of course, I draw here only two of the relations. There are more relations, binary relations that can exist between three entities. So one way you can think about it is, let's try to build a model for each one of the entities involved. So for example, we'll try to build a model for what is Doll, what is Elizabeth, what is North Carolina, and build a model for each one of the relations. And by building a model I'll have some classifier or probabilistic model, and I realize that some of you may not know exactly what I'm talking about, but hopefully you have some abstract idea And as I said, I'll give some tutorials so that will give you a better idea of what I'm talking about. But this model looks at the text and somehow gives me a probability distribution over possible values that DOL can take. And in this toy example, what I show is just a probability distribution over 3 values. So DOL can be either a location with probability 0.1, or a person with probability 0.85, or some other type of entity with probability 0.5. And the same for Elizabeth, probability distribution over possible values. Of course, I have probability distribution over other things here, but I don't show it. Every token, in fact, has a probability distribution over it. And the same thing for the relations. So the relation between E1 and E2, it's a directional relation, could be either irrelevant relation, there's no relation, with probability 0.05, or the relation spouse of, or the relation born in. And what I can do with these models is basically choose the highest value in each one of them, which is colored here in blue, and make a decision. You could immediately see that these decisions, for example, if you look at these 3 squares here, they don't make sense, because I have 2 people, and the relation between them is a born-in relation. It violates some natural constraint that you may have, and we want to change it. So in this case, I'm going to change it by changing the entity value here from person to location. Now everything makes sense. You can also look at these 3 squares, and you can see again that I have 2 people, and the relation between them is born in. Again, doesn't make sense, and I want to change it. In this case, I'm going to change it by going to the subpar decision here, and I'm going to choose spouse of as the relation. Now it makes sense. Of course, here I just made some decisions, and the question, of course, is how do I guide making these kind of decisions? So first, let me say that this actually works better. If you know how to do these things, and you know how to do what I call your inference over your learned models, you can improve the results quite significantly. And one other observation here is that these decisions are not sequential decisions. So you don't look only at consecutive things that happen in the sentence, which is a more typical process that people do in natural language processing, but rather you look at the sentence as a whole, or sometimes a paragraph as a whole, and take into account constraints that could be non-sequential. Of course, the key here is, how do I guide this global inference? Why did I choose to change the location, the entity type here and the relation type here? And another question that you can ask, why did you start even looking at each one of the components separately? You could have learned everything together, and maybe you won't run into these kind of problems. So of course, I'm going to address some of these issues. A very easy answer that isn't satisfactory, but still is an easy answer to this last question here, is that sometimes I just cannot learn jointly, just because I don't have all the components together at one time. If you think again about the puzzle that I gave you at the beginning, or the story that I showed at the beginning, a lot of tasks are involved in addressing these issues. You can't argue that you've learned everything, or you learned how to make a global decision together. You probably learn different components at different times, different circumstances, and different contexts. So this problem is a sub-problem of something that is called, in natural language processing, structured output problems, where for each instance we have a set of variables that we care about and we want to assign values to, and we know that these output variables depend on each other. Many tasks have this nature, from parsing, semantic parsing, summarization, transliteration, and task in information extraction, like entities and relation, which I just mentioned. Of course, there are several direct machine learning or pure machine learning approaches that exist to address some of these problems, like hidden Markov models, conditional random fields, or structured perceptron and SVM. Again, some of you have no clue what I'm talking about, I assume. Some of you understand it. But if you try to use some of these pure machine learning approaches, not all the time you get what you want. So here is an example, another example for information extraction, where this is a citation, and given this citation, I'd like to parse it, which means I'd like to figure out who's the author, what's the title, who's the editor, what's the book title, and so on. If you run an HMM on this data, this is what you get. Train on a rather small number of examples, but still, you can see that it's very bad. It basically violates a lot of natural constraints that all of us have with respect to the expected outcome here. How can we improve it? So again, there are several direct, pure machine learning ways to improve something like this. Basically move to higher order models, higher order HMM, CRFs, increasing the window size, basically increasing the number of features that we look at, basically increasing the model complexity. And this will require, of course, that we'll use a lot more training example when we learn these kind of models. What if we don't have many examples? We only have a few labeled examples. What are the other options? So my goal here is, in this specific example, is to try to keep the learned model simple and still make expressive decisions as required by the problem. And what can help here is the observation, the simple observation that when you look at it, you see immediately that it's bad. It doesn't make sense. It really violates some natural constraints. For example, it violates constraints that you have with respect to where the punctuation marks could be. Or it violates constraints with respect to the fact that you know or you expect that every field will be a consecutive list of words and every field can appear only once in a citation. This is something that we know about citation. And there are a small number of very easy to express pieces of knowledge. By the way, these are not propositional in the sense that they actually use quantifier. They're implicit here, but really you say every field has to have this property rather than field of this type and field of this type and so on, or this punctuation mark or that punctuation mark. You really use hidden quantifiers here. And the interesting thing is that for this example, if you actually enforce the constraints, or even softly enforce the constraints, you get correct results. So again, we're looking for a paradigm or a model that will allow us to do these kind of things. And with these two examples, I can now move to formalizing what we're doing. So we have a collection of variables, y1 through y something. And each one of the variables comes with a probability distribution over possible values it can take. There is another large set of variables, which are the features that I'm using in order to learn this probability distribution, conditional probability distribution over the y values. But these are observed, so I don't care about it. I don't need to set, to assign values to this. I can let them go from this picture. And another important issue here is that I'm abstracting here a little bit. Each one of these y variables could, in fact, be a structure in itself. Could be an HMM or some other structure that basically means it could take many, many values. So the probability distribution is going to be over a large number of values. But for the purpose of this discussion, I can actually abstract this away. I have a variable here that takes some number of discrete values. So in addition to this conditional probability distribution, I also have a collection of constraints over subsets of these variables. So you can think about these basically as Boolean functions over a set of variables that basically constrain what possible assignments they can take. So perhaps y1 has to be different than y4. Or in this constraint, among y2, y6, y7, y3, and y8, at least two of them have to take the value 1 or something like that. And possibly you'll have weights on these constraints. My goal is, given this, to find the best assignment, the assignment that achieves the highest global performance, and best has to be defined somehow. Already, this is an integer programming problem because my variables here take discrete values, integer values. I'm going to make it an integer linear problem by defining my objective function to be the dot product of the probability vectors and the y variables subject to the constraint C. And if I want to put weights on the constraints, I'm going to model it also linearly, and I had the component of w dot product with the set of constraints. A little bit more formally, this is the problem that I want to do. I want to solve an argmax problem over y, which is a vector of variables I care about, of lambda, which is basically a weight vector for the local models that I learn, and f of xy, which is a collection of classifier log linear models or other models that I learn. In many applications, this f of xy is actually going to be only f of x. It will not depend on other y values, but in general, it will depend on other y values. And I want to solve this argmax problem subject to some constraints that I'm also going to model linearly. In this case, what I have here is a collection of constraints weighted by these row i's that you can think about as penalty for violating the constraints, and this distance function between a solution, a proposed solution y, and a characteristic function that depends on the constraint basically tells me how far is y from a legal assignment. And I want to weigh this distance in order to change my objective function here. So this is really the formal problem that I need to solve here, and immediately it brings up two computational problems. One of them is how to solve this problem. It's an integer linear program. I could solve it directly using some commercial ILP packages. I can use search technique in order to solve it. And another problem is how to train these models. And again, there are several questions here. One of them is, do I want to train together the learned component, the left side of this objective function, and the constraints, the right side of it? And even more, do I want to decompose this global objective function to multiple components and train each one of them separately, or do I want to do everything globally? And there are several interesting issues and difficult issues in trying to figure out what's the right way to do these things. Okay, so I'm ready now to give you a slightly more detailed example that will allow me to move to some details. So the detailed example is going to be in the context of semantic co-labeling. And this is the problem of parsing sentences semantically, or the shallow semantic level, at the level of who did what to whom, when, where, why. So given this sentence, I let my pearls to my daughter in my will, I'd like to be able to parse it and figure out that I am the lever, my pearls here is the things left, to my daughter in this case is the benefactor, and in my will is something that is called here a location argument. So you can think about this problem as basically a problem of chunking a sentence to arguments, and there are many, and then typing them, coloring them with some color. Of course, there are many ways to chunk sentences into colors, into chunks, and color them, and some of them are legitimate chunking, and some of them are not legitimate. For example, they could be non-legitimate because in this formalism I don't allow overlapping arguments. There could be non-legitimate because in this formalism, for example, I know that if argument of type A2 is present, A1 must also be present, and some other linguistic or other constraints that you may have. So again, this is a structured output problem because there are multiple decisions that I have to make and they interact. This is a special case of the structured output problem because in this case, I actually have data that allows me to learn everything together. I don't need to learn each one of the, with respect to each one of the arguments separately, although I would actually do that and argue later on that that's the right way to do it. A little bit, just to give you an idea of what type, how people do work in this area. We have a collection, data collection, a rather large collection of data. In this case, it's 1 million words, not so large in today's paradigm, but it's an annotated data, because the work, the annotation work, which is very difficult in itself, was done by Martha Palmer and colleagues. And they basically gave us a corpus that annotates, as I said, 1 million words from the Wall Street Journal with respect to this formalism. The annotation types different arguments at the level that is called core arguments. So there are about 6 or 7 core arguments, like subject, object, and so on, and 13 different types of adjuncts, like location argument, temporal argument, manners, and so on. So overall, this is a large classification problem, because given that you have identified an argument, there are many options to type this argument. How do we address something like this? So the algorithmic approach goes something like this. So you start by looking at all possible arguments. So every consecutive set of words in the sentence could be an argument. So you have n squared candidates. And you start by trying to identify what could be legitimate argument candidates. So you want to move from this picture of considering all possible arguments to a slightly smaller set of arguments. This in itself is a classification problem that tells you this is a candidate, this is not a candidate. Once you have a smaller set of arguments, you move to classify them to type, or color them in this case. And as I said, there's a large number of options. And in this case, I show it as if I color each one of the arguments. In practice, what happens is that I give you a probability distribution over possible colors. It's easier to draw it this way. And once I have this, my final stage is what I call here an inference stage, which is take this input and put it together into one output that makes sense. So you could think about the first process, the first step, or first two steps, as something that identifies new vocabulary. I started by just looking at words in a sentence. Now I have a richer vocabulary. I can talk in terms of arguments and their types. And the second step is some kind of an inference step over old vocabulary and new vocabulary. Research-wise, the first step, which really is a classification step, is easy. We have a very good understanding today of these steps. And therefore, from a research perspective, the interest isn't there. Although this could be very expensive. And I'm going to spend now some time trying to talk about why is this expensive, what are the issues that go into solving this stage. The inference stage is more interesting research-wise, and I'm going to spend a couple of slides just talking about this issue. So what is the inference? So the inference is something that takes as input the output of the argument classifier, which basically is a probability distribution over possible argument types for each one of the arguments, and attempts to find the best legitimate output for each one of them. And this is the problem that we formalize as an optimization problem and solve via integer linear programming. So again, the input to this is a probability estimation that the models or the learned classifier give me, along with some structural and linguistic constraints. More specifically, for each argument A, we can set a Boolean variable AIT that indicates whether AI takes the value T. And given that, my goal is to maximize this sum over all arguments, the score of AI being equal to T, times this Boolean variable, characteristic variable AIT. And I want to do this subject to some linear constraints. One interesting thing about this, that if you think about, or if you have classifiers or models that where the score of AI being equal to T is actually the probability of AI being equal to T, then this objective function really attempts to maximize the expected number of arguments that are correct and satisfy the constraint, which is really what you want to do. In these kind of cases, we don't really care about most likely assignment to the sentence. We care about maximize the number of expected correct decisions, because this is what we're going to be evaluated. People will count how many of the components we got right. And in this case, the constraint conditional model, which I showed formally before, is completely decomposed. Each one of the arguments is learned with its own model. Constraints. So the nice thing about this is that the language, since we enforce it to be a linear model, the question is, can we express good constraints? It turns out that we can express a lot of very important and expressive constraints with this language. For example, I can say that I don't want to have duplicate argument classes. And the way to do it is basically to sum this function over all potential arguments. This is the Boolean variable that says that the argument A takes the value A0, and I want the sum to be less than 1, which means I don't allow 2 to get this value. Or I can say things like, if I have an argument of the type arg, for any value that you can put here in R, could be A0, A1, A2, then I have to have somewhere in the sentence also an argument of type arg. Or I can say that if I have a continuation argument phrase, somewhere before it in the sentence, I have an argument. And it's very easy to understand that you can write these things as linear inequalities. In fact, it's known for a long time that any Boolean rule can be encoded as a set of linear constraints, and basically this is what we're utilizing here. So the language, as I said, is quite expressive. We can say things like no overlapping arguments or no embedding between arguments. We can express relations between number of arguments or order constraints. We could say things like if the verb is of this type, then it cannot take more than k arguments, or if the verb is this, it cannot take an argument of this type, or it must take an argument of this type, and so on. So again, notice that these constraints are really universally quantified rules, although I'm hiding the quantifiers here, but it's important that it is. And one important point here that I'm going to come back to it later, in one of the software packages that we've developed, LBJ for Learning by Java, we allow developers to encode constraints in a very high-level language, essentially first-order logic language, and these are compiled into linear inequalities automatically. So you don't have to think about how do I express something like this as a linear inequality. Okay, so this is the outcome. You can go to my group's webpage and play with some of the demos. This is one of them, where you can type in a sentence like this one, a car bomb that exploded outside the US military base, blah, blah, blah. And you will get this parsing. In this case, identification of two main predicates and the arguments relative to these predicates. And it's important to know not only that this is actually quite good. I think if you play with it and type some sentences in, you'll be impressed yourself. It's also very fast. Even though it's an integer linear programming problem, which is NP-hard, it's rather easy to see that it's fast. You can process about 7 sentences a second, which means that even though the problem is large, and I'm going to get into some sizes later, you can solve it quickly. Okay, so this was now you know everything about this problem, at least. And I want to give some ideas of what are the computational processes that are involved in getting there. And I'll spend most of my time talking about classification. How many of you know what I'm talking about when I'm talking about learned classifiers? Not all of you. Okay. So I'm going to help someone. So we typically think about classification as an ambiguity resolution problem, where you have multiple options, like the first sentence here, that says Illinois Board of Education. There's a spelling mistake there, and it's really not true also, but I saw it on a t-shirt and I couldn't avoid using it. Really, what is meant is this type of board. I hope you agree with me. But the question is, can you write a program that looks at this sentence and decides this is the wrong board here, it has to be this one? Another type of classification, look at this sentence, Nissan car and truck plant, plant and animal kingdom. These are the same word with two different senses, and the context determines which sense it is. We want to be able to learn a classifier or write a classifier that figures out that this plant has some kind of an industrial meaning and this has a different sense. In this case, the problem is to determine for each one of the words in the sentence, this can, will, rust, what is the power of speech tag of the word. For example, if you look at the word can here, in this specific case it's a noun, although the most common power of speech tag of the word can is not a noun, it's a modal verb. This is a decision that you have to make that happens across sentences. The dog bit the kid, he was taken to a vet or a hospital. what does he refer to? Does it refer to the kid or to the dog? It's very easy for you to figure it out based on how I choose to end the sentence. Not so easy to write a program that does that. You need to know something. And another example, if I want to do name entity recognition, I want to figure out that Washington in the context of this sentence is a location, tiger in the context of this sentence is a person, although maybe 10 years ago tiger wasn't a person. So things change. And again, simpler problems like given a news article, you want to know whether the topic is finance, banking, world news, sports, and so on, or whether you like it or you don't like it. So these are all classification problems. And the important thing about it is that we don't know how to program these decisions explicitly. These decisions really require you to know a lot of things from the context and perhaps something that you have to bring from home. It's already known in this area that for the last 15 years or so, that the only way for us to get robust or relatively robust decisions for these kind of problems is to use statistical machine learning methods to learn these mappings. So what kind of mappings are we learning here? So really the goal is to learn a function, f from x to y, that maps observations in a domain to one of several categories. For example, in the case of Illinois Board of Education, I have two categories, and I have to decide which of these words fit better in the context of this sentence. So the typical learning protocol is going to be, give me a collection of labeled examples, pairs x, y, and use it to learn a function f from x to y that is consistent or almost consistent or relatively consistent with the observed example, and then hope that this function is going to do well also in the future. Of course, this hope today has some theoretical guarantees, but basically that's the paradigm. So as I said, the goal is to learn this function, and let's think about it for a minute as just learning a function that maps into two categories, positive and negative. In this case, I can think about all my data as being thrown into some space that has points of two colors, positive examples and negative examples, color purple and red. And my goal is to actually separate them. How do I separate it? I could separate it with this curve, I could separate it with this one or with this one. So one of the key questions here is, what function do I choose in order to separate the data with? And the decision, for many good reasons, is that what we learn is typically linear functions. So our decisions is going to be, if x is the data representation, my classifier is going to be a weight vector w, and my decision function is going to be the sign of this dot product wt dot x. And that's what we're doing in machine learning for some good reasons. Of course, you can say there could be some expressivity problems. Why do you think that linear is good enough? That's one key problem. Another one would be, well, there are always multiple options. How do you choose which of the linear options to choose? And once we address these issues, the question, of course, is how to find a good separator. So to the first question, expressivity. Of course, we know that linear isn't enough. I mean, take the XOR problem. We know that given a space, not all functions, in fact, most functions are not linear over this space. So what do? We make functions linear. So if you start with this picture here, where deciding whether the word to use in the sentence is this kind of weather or this kind of weather is a non-linear problem over my current space. For example, maybe it's expressed as some non-trivial DNF function. What I do is I'm going to transform my space into a new space, and the way I'm going to do it is by inventing new variables. Perhaps I'm going to invent variables that are conjunctions of size 3 of the original variables. And in this new space, I have a functionally simpler function. Now I have a linear function, but over a much, much higher dimensionality. So an important outcome of this view is that we deal with high dimensionality. Typical problems that we deal with have order of magnitude of 10 to the 6 million features, and this is where we have to run the algorithms. So I'll get to it. I'll give specific examples to features. If you prefer to think about it in a continuous space rather than this discrete space, think about this. So here is a function. Here's a collection of points. And I want to separate the blue points from the red points. Of course, I cannot do it if I insist on a specific class of function. I can do it with this kind of curves, but I cannot do it with linear functions. However, if I move to the x square space, so every point now is mapped to x, comma, x squared, now I can separate it with a linear function. And again, with this example, of course, the key issue is going to be what are the features? And I'm going to address it in a second. And one of the interesting problems that we have in this domain that we don't have a principal way to decide which features to use. However, computationally, there are many ways to do this mapping. Some of them are implicit via kernel, some of them are explicit, and there's a well-understood trade-offs between what to use when. Okay, so we are done with expressivity, and I want to address the issue of there are multiple options every time. How do you choose? And this issue goes under what we call regularizations. Among several options that are consistent or pretty consistent with your data, choose the simplest one. That's the guiding principle, and of course there are reasons to do it that we can justify. And in fact, even the fact that I decided to learn linear functions rather than higher order functions is a form of regularizations. But I'm going to give a simpler example. Assume that I look at this data of blue points and red points, and there are two instances here. And these are linearly separable, but they are linearly separable in two ways. On the left, I separated it with this thin line, and in the right, I was able to tilt the line a little bit and separate it with a thicker line. Which one is preferred? And the idea is that the right one is going to be preferred because it's a thicker line, has a wider margin. So this is a form of regularization. There are many ways to regularize, and as I said, there is a good understanding today of how regularization drives better generalization, because this is really what we want to do. I mean, there are many ways to be consistent with the training data that we have. The question is, can we say something about which of those is going to do well on examples that we haven't seen yet? And this is really the key reason for regularization. Putting this together, this is the problem that we have. We want to learn classifier, basically find a weight vector, W, such that it minimizes the sum of the empirical loss, how well we're doing on the data we've seen, and the regularization term. Both of these are functions of this W that we're after. And the loss could be many things. It could be the number of mistakes we're making on the data, or it could be some kind of L1 or L2 losses, or it could be some kind of log loss that is driven for maximum likelihood or any other probabilistic interpretation. There are different functions that we can define as loss. And regularizations could be different. Could be, you know, L2 regularization, L1 regularization, and we know that each one of them actually has a different goal. I mean, one of them could be minimizing margin, another one could drive us more to a sparse solutions, and so on. So there is a pretty good understanding of what's the role of, or even when do you want to use which. And algorithmically, again, there are many solutions that we have, from online solutions like the perceptron family to gradient descent algorithms or stochastic gradient descent algorithms to SVMs. And we also have a pretty good understanding of the pros and cons of each algorithm. It's well understood today that all of them will converge to about the same solution, but there are trade-offs in terms of computation time, number of examples required, and efficiency. So now you know everything there is to know about classification. And this was just to back up my statement before that It's easy. I mean, it's very well understood. Theoretically, we understand it. We have generalization bounds. Algorithmically, we understand it. We know how to deal with very high dimensions. And we are very efficient between linear and quadratic, depends on which algorithm you like, in the number of examples. In terms of parallelizing it, data parallel is very easy at evaluation time. We don't know how to do this at training time. Okay, so as I said, it's well understood. What's still left? So there are several issues that are left with respect to training protocols. I'm not going to talk about it. The key issue that is left is features. And I do want to talk a little bit about features to answer the question and to make things a little bit more concrete. And also because computationally, this is something that is typically is a secret in the machine learning community. People don't admit that most of the time, both engineering time and computation time, is being spent on feature extraction. So it takes time to think about what features work. And moreover, feature computing or extracting features is by far the most time-consuming process. Why is that? If you think about what kind of structures we deal with, it will give you an idea for what are the difficulties here. So there are several different kinds of NLP structures that we deal with. From simple sentence representation, where I want to know which word should I plug in here, whether WH or whether WEA. In order to decide these kind of things, I should extract features of the form the word no appears before my target word. The word to appears after it. The conjunction to laugh appears after it. The conjunction to and then verb appears after it. There's a verb before it and the word to after it, and so on. Now, if you think about it, the word whether, W-H-E, can take many, many words around it. And if there are 50,000 words in English, and you take combinations of words, pairs of words that appear before and after, already here you will get order of magnitude of 50,000 square. Of course, most of them will not appear. Nevertheless, you will get easily hundreds of thousands possible features that can occur in this context. Most of them are unimportant, but you have to figure it out, so you're going to represent all of this. Second type of structure, when we deal with sequential problems, we typically, for example, if we want to solve the name entity recognition problem, I want to know that this guy represents a person, this represents a location. The encoding that we're going to give it is, this is the beginning of a phrase, this is inside a phrase, this word is outside a phrase, outside a phrase, outside a phrase. This is a unique phrase, just a single word phrase. This is just one of the possible encoding that I can use for sequential structures. What kind of features do I take here? Typically, we will take features that are pairs of states, consecutive states, or pairs of states and words, observed words. Again, there are going to be many of these kind of kinds. And many times we represent things as trees. I didn't talk about how we get trees. Learning trees is one of these structured problems that I'm not going to talk about today. But nevertheless, if we do have a representation of trees, the type of features that we want to extract, given a small tree, not necessarily as small as this one, I want to know how many times does this small tree appear in my sentence representation, or whether it appears in my sentence representation. And again, A, B, and C typically would be either words or non-terminals, names of phrases, and so on. And with all this together, I will have, again, irrespective of what representation you have, I will have a lot of features, because they depend on the number of words in my vocabulary. And computing a feature, or taking a sentence and converting it to its feature-based representation, is really a process of some kind of subgraph isomorphism. It's quite expensive, and you have to do it for every instance that you see. Okay, so now you understand the process that I discussed before about identifying, classifying, and you also understand why I said it's easy. We understand it. Hopefully you understand also that it could be very expensive. one more stage that I want to talk about. So the way I describe it here, you have a classifier. The input to the classifier is typically not the sentence itself, but rather classifiers that you've learned previously. So really there's a pipeline. Most of the problems are not single classification problem. We start by looking at the raw data, learning parler-speech tags, and then we believe the parler-speech tags and use it to extract features to learn phrases, and then semantic entities, and then relations, and so on. So there is a pipeline of processes, each one of them of the type that I described, of a large classification problem. So there are interesting conceptual problems here. We all know that pipeline isn't necessarily the right way to do it. It's a crude approximations, and there are interesting research questions here. Some of them we deal with, but I want to address the computational issues. Clearly, some of you guys know how to deal with pipelines better than we do. And in fact, in NLP, no one is thinking about how to do it right. There's a lot of room for improvement in the computational process just from this perspective of pipeline. Okay, and finally, let me say one more word about the inference. We went over this slide in details. What I want to say is something about the computational issues that are important here. So clearly, this computation of the integer linear programming or the search problem that you want to solve is dominated by how many variables you have and how many constraints you have. Typically, we'll have just a few hundreds variables or constraints, but the important issue here is that inference is done per instance, per sentence. For every sentence, you set up an inference problem by running your classifier and have to solve the inference problem. So if you have hundreds of thousands of sentences or millions of sentences, this is where the time is going to go, not necessarily for each one of the instances. And what saves us here at a single instance level is the fact that there are many issues of sparsities here. By sparsity here, there are several notions of sparsity, but one of them is the fact that even though I have many variables, only a small number of them are active in each constraint. And therefore, even commercial ILP packages could do quite well in these kind of cases. Okay, so I'm not going to talk about the training paradigm. Took a little bit more time than I thought. And in fact, I'll skip over this example also. And let me summarize and see if I can have some question that I can respond to. Okay, these are things that I wasn't gonna. Okay, so basically, I talked about constrained conditional models, which is a framework that allows you to see what kind of processes go on when you try to solve a natural language processing problem, a large NLP problem. Basically, I talked about learning conditional models and the notion of using constraints on top of these learned models. It's a nice framework that allows people, not only in NLP, but in particular in NLP, to incorporate in a clean way constraints to bias global decisions in the way so that they satisfy some plausible constraints. And it has significant success on a large number of NLP and information extraction tasks. I was trying also to give you a tutorial on computational issues in machine learning and inference. Hopefully, some of you that came without this knowledge know a little bit more about what are the issues. And I want to end with a shameless plug to a package, one of the packages that we are developing in my group that is called Learning-Based Java. For those of you who are interested in using machine learning for your own purposes, this could be a good way, an easy way to enter into this domain. It's a modeling language that allows you to program along with building learned models and allows you to specify constraints and in fact even learn models in a rather high level, so you don't necessarily have to be an expert in machine learning or inference in order to do it. And with this, let me end here, take some questions. Thank you.
So Dan, one of the reasons why we have this seminar series is to try to figure out what are the application level goals that one can accomplish, if we drastically reduce the time of processing? And understanding natural language, to me, is not a real application. To me, the real application is what you do after you understand the natural language, such as translation, such as some kind of automatic term paper writing or something for students. So what are the application level goals that your community is trying to accomplish, such as being able to automatically compose a term project before the deadline is passed?
We don't try to do that. I mean,
Dan, would you mind repeating the question for anybody watching?
So the question is, what are the key application domains? So let me give you one generic application, and hopefully you will feel. So in fact, so one of the tasks that I like, and I think it's really a generic application in the sense that it's only your imagination what you can do with it, is something that is called textual entailment. So the idea in textual entailment is, here is a piece of text. Look at the left here. Eyeing the huge market potential, currently led by Google, Yahoo took over search company Overture. The question is, does this mean that Yahoo acquired Overture? So this is a fundamental problem. I want to know whether this means that. When you read the newspaper, you solve this problem every sentence that you read. On the other hand, this has a huge amount of applications. For example, application to search. Rather than keyword level search, I want to write as a sentence, acquisition by Yahoo, or Yahoo acquired someone. Today, what I will get is just basically junk, things that mention Yahoo and mention acquire, but the context could be different. If I understand that this paragraph means that, and other paragraphs that don't even mention Yahoo perhaps, or don't mention the word acquire, which this one doesn't, then I'll be able to search better. I will be able to access information in a much better way. I will be able to build application like, allow kids to read books electronically, click on a sentence, ask a question. I will be able to understand instructions and do something with this instruction, or have my machine help me understand things because it has read the instruction and I typically don't read instructions. I don't know about you. So this is a key application, or you can think about this as an engine for a lot of applications, including summarization, including translation, including a lot of multilingual type of problems, and so on.
So this is great. So so what's the reality of this kind of activity? Is it 1 minute per page today, or is it 10 days per page?
Okay, so the process that I described before, which was the semantic parsing, is one ingredient here, one of the important components in doing this. So there are two issues here. First, we don't know how to do it well. There's a lot of research that goes into, let's figure out how to do it. And the type of research is basically what I described before. There are many sub-components that we're trying to do, and we also try to figure out how to put it together to this kind of... Now, today, we have a system that addresses this that I think takes about maybe a minute, or order of magnitude of close to a minute, for each decision. So give me a paragraph, 5 sentences, and give me a short sentence. Ask me whether this sentence holds there, and it will take almost a minute to do something like this.
Or like a typical paragraph.
Yeah. So now take into account that we haven't worked very hard in order to improve the time. But so I think you can help us easily to cut it by a factor of 10. And this would be useful, right? Or even just the task that I described before, semantic or labeling. If we could process the web at that level, which is impossible today, unless we figure out how to, use parallel in a better way. Some back of the envelope computation that I did shows that we can, if you give me 1,000 strong machines, we can probably do it, or the good part of the web, say 1 billion pages, in about 2 to 3 weeks. And now, if we can give a service like that to people, they can do many things. They can access the web in a much better level than is possible today. Yes?
Follow up on that question. So I think the key idea is to take those types which are currently only done in the batch mode and make them interact. So what would be some other examples? I would imagine like in the spell checking, you don't want to wait like when you load the document, you don't want to wait like 5 minutes because you're out of the context. You want, for example, with the video import, you want that to be interactive like as you type, right?
Yeah, of course. So in this case, there's an issue of time, there's also an issue of space. Because today, the classifiers that we have for these are very large. We have to think about how to compress them significantly and still keep the performance good. Yes?
So, Dan, in the system that you described, does the number of constraints grow in the integer program as you parse through text?
No, every sentence is a different inference problem. So okay, for computational reasons, all the work that is done today in NLP is sentence level. In many cases, we want to be able to work paragraph level or document level. Very little of our work is done at that level because of computation. But specifically to your answer, no. To your question, no. I mean, we just process one sentence at a time, and the length of the sentence determines the size of the inference problem. So if it's 30 words or 5 words, it's going to be a different size problem.
Right, so, but if you wanted to extract meaning from a broader sequence of sentences, would you want to increase the number of constraints?
Yeah, and I want to increase the number of variables also. And it will increase as the size of the piece of text I'm studying, I'm analyzing will grow. Yeah, of course, the interaction is going to be weaker, right? Because typically things that happen at the beginning of the document are less important to the end, but there are interactions, of course. And today we take them into account in a very crude way because of computation. Yes?
So I have a question. So today there are two groups of people. So first group is a machine learning group of people, but they don't have interest or they don't know how to do the high performance computing to speed up your application. So the other group is they are doing high performance computing, but they don't have enough knowledge in your specific domain. So do you have some suggestion to how to bridge the two groups of people? So today the map reviews computation framework may be a solution. So do you know something?
Yeah, okay, so the question is how do we bridge the gap between people that do machine learning or NLP and people that understand parallel and high performance computation? And it's a good question, that's why we're here. So far we weren't that successful in this, but the idea, the hope is to find students that are interested in both and are willing to do this, to make progress in this area. I mean, that's what we're trying to do. I think this is, I think it's very interesting because there are many, many interesting issues. So MapReduce that you mentioned is possible solution to some of the problems. Not all algorithms can be addressed using MapReduce paradigms. You'll have to invent new things.
Let's turn this on. If there's anybody online and you have a question, you can feel free to enter it into your browser window. Anybody here in the live audience want to ask a final question?
Yeah.
Okay, so do you think actually the precision of your technique, it very depends on the base knowledge or knowledge base? knowledge base is larger, where the precision be increased. If it is true, then where this also imposed as a computation intensive task. For example, for the same sentence, but this time you use the a very very large data knowledge base, then you may need 1 hour to get the result, but the precision is double.
Okay, it's an interesting question. So the question is, to what extent the accuracy of the techniques that I'm talking about depend on the size of the data? And typically we think about it as the size of the training data that we use to train our classifiers. But in fact, you can think about more than that. You can also think about some knowledge bases that give you some background knowledge. What's the impact of the size of this knowledge? And it's known that this is important. You know, the number of examples you have to train on is going to have a huge impact on the accuracy of your classifier. But it's also known and even admitted today by companies like Google in their translation efforts that data isn't enough. You need to look into some better theories of how to look at sentences, how to analyze text, and just training on larger and larger amounts of data is not going to do it. It's going to help, but it's not everything.
So generally speaking, with more computing power, it generally gives better results, but there may be a limit which is imposed by the theory, right?
Yeah, this could be a good summary.
Okay, any questions from online? Nope. Thank you, Dan. Very nice to meet you.
Thank you.